Hello, you are welcome back once again. So let's solve some couple of examples about how we can find the velocity and the distance from acceleration. So the first example that we want to look at in this tutorial is as follows. Suppose that a of t, which is the acceleration, is equal to 12t power 2 minus 6. This is the function. That's the acceleration function. A of t equal to 12t power 2 minus 6 with v of 0, which is an initial condition being given. That's the initial velocity. The initial velocity is 5, right? We have been given that our v of 0 is the initial velocity and is equal to what? 5. So that means v of 0 is 5. And x of 0, which is our initial distance, is also 10. Our initial position is also 10. Then the question is, we should find the distance and then the graph of a of t, v of t, and then s of t. So this is quite a little bit long example because we need to also learn how we can come out with the graph, and I think that coming out of the graph is not other difficult. So I'm hoping that you get to understand it properly or well. So let's move on and solve this example. Now we have these parameters. We have the acceleration function, we have the initial condition for the velocity, and then we have initial condition for the position or the distance. So if we want, the question is asking us to find a distance function. So that means that when we pick the acceleration function, we need to integrate it. And when we integrate it, we are going to get 12t power 3 over 3 minus 6t. And don't forget that we need to introduce our first constant, which is c1, which is the arbitrary constant of integration. So in doing this, now we have our velocity function, which is what? V equal to this. Now they are telling us that our velocity function at v of 0 is 5. So we can say that 5 is equal to 12 divided by 3 will give us 4t power 3 minus 6t plus c1. And then they are saying that v of 0 here, so wherever we see t, you should plug in 0. So 5 equal to 4 0 power 3 minus 6 0 plus c1. And at the end of the day, we are going to get c1 equal to what? 5. So that is our arbitrary constant of integration for the first integral. So let's come to the second integral. When we come to the second integral, now our main function, the velocity function, becomes v equal to 4t power 3 minus 6t plus 5. Right, that will become our velocity function. So now that we have a velocity function, let's integrate it once again to get our distance function. So when we integrate it from both sides, we are going to get s of t to be equal to 4t power 4 over 4 minus 6t squared over 2 plus 5t. And don't forget our arbitrary constant of integration, which is plus c2. And based on this, we can further simplify it to get s of t to be equal to 4 will cancel 4. We have t power 4 minus 3t power 2 plus 5t plus 6c2. That's our constant. So we have been given that x of 0 equal to 10. It means that the initial condition when t equal to 0 is 10. Therefore, we can do the substitution, which is 10 equal to 0 power 4 minus 3 0 power 2 plus 5 0 plus c2. And at the end of the day, we are going to get our c2 to be equal to 10. And therefore, bringing it back to the original function, we are going to get s of t to be equal to t power 4 minus 3t squared plus 5t plus 10. So this is our distance function. So the next thing is, let's look at how we can come out with a graph. That is very important. So let's take a little bit of time and see how we will be able to come out with a graph of these functions. Now, let's see something here. Let's take the first one to be the acceleration function, a of t, which is 12t squared minus 6. Now, if you have to use a technology, this is something simple that you can just use GeoGebra or your calculator to just solve it. But maybe your lecturer is going to tell you that you should use your hand in plotting this, and you should know how you will be able to come out with such graph. And I'll be doing a lot of examples with you when I get to the other application, which is the area between and under curves. We will talk more about how you will be able to come out with a graph given you, or given that you have been given the function. So as soon as you see this function over here, you should get to know that it is going to be a quadratic function. It is totally going to be what? A quadratic function. So let's look at how we are going to plot this example. So first of all, one thing that you can do is that you need to find the turning point. And at the turning point, the differential of the acceleration velocity is going to be 0, as you did in your calculus 1. So the turning point is, when we do the differential, we're going to get 24t equal to 0. And now we are going to get t equal to 0. So let's take it this way. Assuming that our a of t is equal to y, let's assume that way. We are going to get, I want to use letters where you are not going to be like confused, but we can also use it that one as well. And assuming that our t also represents our x. So if you want to remodify this, you can rewrite it as y equal to 12x squared minus 6. I hope you understand this one very well. And I know this is the one that you have been using to draw most of your graphs since you are senior high school. So based on this, you can say that at x equal to 0, at x equal to 0, your y equal to negative 6. And at y equal to 0, your x equal to 6 over 12, that will be square root of it because we are using this function, and at the end of the day we are going to get square root of 1 over 2, and you can simplify that as well to get the values of 1. So let's say 1 over root 2, and you can use a calculator to find that out. So now your points that you are going to plot for now, it's going to be 0 and negative 6, and that of 1 over square root of 2 and 0. And therefore, if you have a graph like this, at x equal to 0, y is 6, negative 6, you have it here. And then you are going to have an x value also here. Let's say here to be the 1 over root 2. And since it's a quadratic function and also a minimum function because the coefficient here is positive, we can plot it like this one. So you can use GeoGebra to basically draw this to see how things will appear for you, to see whether you are right here or you are not right. Same thing applies to the velocity function. So I would advise that you try your hands on it and then you use GeoGebra to confirm your answer over here because of time. And therefore, I will say that we are going to tackle how we can come out with a graph manually with our hands in Minus tutorials. So look out for it on how you can come out with a graph with your hand in order to solve an area bounded by 2 curves or 2 or more curves. So this one, the velocity one, you are going to get a graph like this, but it's not going to touch the origin yet. And then the last one, you are also going to get a graph like this, which is the distance function. You are going to get a graph like this here. So please use the same procedure or approach, and then use GeoGebra to confirm your answer, and then look forward for my next video. We are going to tackle it on how you can use your hand to come out with a graph in order to help you find the area bounded by either 2 curves, 1 curve and the x-axis, or any other function that will be given in a question. So thank you. But it seems I'm not done here. Let's with the last example. Let's quickly finish it up and see how things will go. The last example talks about the driver. Let's come in here. It talks about a driver traveling at 40 miles per hour which is 58.67 feet per second, applies the brake softly at first and then harder, coming to a complete stop after 7 seconds. The velocity as a function of time is modeled by the function v of t equal to negative 1.197 t power 2 plus 58 power 2 plus 58.67 where v is in feet per second, t is in seconds, and the range is between 0 less than or equal to t less than or equal to 7 seconds. And we are being asked how far did the vehicle travel while the driver was braking. So this is as simple as that. So the distance traveled is given by the definite integral v of t equal to integral of 0 to 7 into bracket of the function negative 1.197 t power 2 plus 58.67. And remember, it's dt because we are integrating it with respect to t. So since you understand your integration, you are going to just do your normal integration. You are going to get negative 1.197 over 3 t power 3 plus 58.67 t. And our limit of integration is going to be 0 to 7. And doing upper limits minus the lower limits of the fundamental theorem of integral calculus, you are going to get negative 1.197 over 3 multiplied by 7 power 3 plus 58.67 multiplied by 7 and minus the lower limit, which is what, 0, because when I put 0 inside all these functions, since they contain the variable t, they are going to give me 0. And at the end of the day, I'm going to get my distance traveled s to be equal to 273.87 feet. So this is nearly the length of a football field. So in the graph of x, the shaded area will represent the distance the vehicle traveled during that particular 7 seconds. So thank you for watching. See you in my next video.